Fourth and final conic section, hyperbolas. So hyperbolas are the most different of all of the other conic sections, as they aren't really ever dealt with in math other than in this very specific section. Parabolas are the sort of basis of Algebra 2. We spend a lot of time dealing with quadratics, which are the formulas that give us parabolas. Circles and ellipses, we find those in geometry as well, but hyperbolas are very, very specific and particular to this section of math dealing with conics. So if you've never seen one of these before, a hyperbola is basically, it looks like two parabolas that are opening in the opposite direction. So this one is opening left and right, but they can also open up and down, just like a parabola can open in any of those four directions. So if we have opening left and right, that's going to look as one set of equations and then a very similar set for if it's opening up and down. The same way the parabola equations were similar, in the same way the ellipse equations were similar. Whatever the direction it's opening, that's going to have a bigger value. If it's an x value, it's opening left and right. If it's a y value, it's opening up and down. So we'll take a look at what those formulas are in a second, but first we're going to talk about all of the different parts that are on hyperbolas. Now, most of these have shown up, well, a few of these have shown up in other places, and then we have a few different words that we've maybe seen in other parts of the pre-calc or Algebra 2 sort of coursework, and then maybe some new words as well. So the first thing is vertices, and vertices are something that we've dealt with in the parabolas, so these are very similar to parabolas. Center, we dealt with that in circles and ellipses. And then we have foci, which we also had in parabola and ellipse. So those words are all familiar, and we've done all of those before. But there are, like I said, a few new things on here. So the first that you might see there on the left is a transverse axis. So a transverse axis is the line that's going through all 5 of those points that I just mentioned. So going through the center, going through the 2 vertices, and through the 2 foci. So transverse, to travel through, kind of like traverse, transversal, the line that went through 2 parallel lines. So all of that sort of terminology might be familiar with us. So transverse, it is going through everything. We have the red dotted lines, which are asymptotes. Asymptotes have shown up a bunch of different places in terms of graphs in this coursework. We had them when we were dealing with rational functions. We saw them in trig, so those are nothing new. They're just regions that sort of bound the graphs. And then in the middle there, written up and down, is that word is conjugate, C-O-N-J-U-G-A-T-E, conjugate axis. So the conjugate axis only goes through the center. Easy way to remember that, conjugate, center, they both start with C. So that one is not as important. It doesn't do as much for us, doesn't tell us as much, but it is going through the center. And the reason why it's there, it's very similar to the directrix from parabolas. It is the line that is equidistant from the center to the vertices, the center to the foci, and the center to the curves. Okay, so those are all of the different parts we're going to have. Those will be important when we go to graph these. Here are what the equations look like, and they both look very similar, so you'll see the first one here. This is for a hyperbola opening left and right, like the picture we have above. So when it's opening left and right, x is going to be the dominant number, I guess, if you will. The a number will be bigger. So that is first, not necessarily bigger, I'll take that back. The x value, though, is first. The other big difference here, and I mentioned that at the top, we have a subtraction. That has not happened in any of the conics yet. The circles and ellipses were squareds plus equals 1. These are now squares minus equaling 1. So this is basically like taking an ellipse, but not doing top and bottom, doing like left and right of the ellipse, and then flipping these pieces outwards. So sort of rotating this by 180 degrees each piece, and then we get something that looks like this. So that's what the subtraction does for us, is it turns that ellipse outward. So instead of opening towards each other, they're opening away from each other. Okay, so here we have all of the information for left and right oriented hyperbola. It has a horizontal transverse axis, which is what we see right here. The center, that's the same as it's been for all of these. The center or the vertex or whatever the middle point is has always been the same, h and k. So the vertices are h plus a, so that is familiar. Then the foci are h plus c, also familiar. The transverse axis is y equals k, so that is the line that is running horizontal. So y equals line, and then the conjugate axis, what I've got there, c axis, is the line x equals h, so going right through the middle. Then the asymptotes. The asymptotes are linear equations, and they are on a slope, so that's where we get this equation from. This is point slope form, so it's y minus k equals plus or minus, so there's two lines, positive sloped and negative sloped, b over a, h minus x. And now we get this a, b, and c relationship, and it's the way that we've seen it everywhere else. This is the Pythagorean sort of setup to it, which is different from the other shapes. So the subtraction symbol is in the center vertex formula at the start, and now this ABC relationship has the plus sign. So all of this stuff looks exactly like the ellipse. We've just traded the minus sign from the ABC relationship with the plus sign in the kind of setup piece. So make sure you keep those two things straight. To quickly talk about how to differentiate what the conic is going to be, we can do that based on the formula that we get. So going back to the first set of slides here that I had for the parabolas, the way to tell that it's going to be a parabola is only one quantity will be squared. And we can see that in both of the formulas, there's only one squared set of parentheses. So parabola has one set of squared. Either the x is squared or the y is squared, but not both. For ellipses and circles, the way that you know it is an ellipse versus a circle, an ellipse will be x and y squared over numbers. So the x quantity squared over a number, y quantity squared over a number. They'll be added equal to 1. For a circle, there won't be any denominators. It'll be x quantity squared, y quantity squared equals some number that is not 1, so some bigger number, likely a square number, like 25 or 49. And then for a hyperbola, it's the only one that has subtraction. So as soon as you see subtraction, it's hyperbola. So that's what you want to look for. One thing squared, things squared added in denominators, that's ellipse. Things added equaling a bigger number, that is a circle. And then things subtracted, that is a hyperbola. Okay, so let's get into the examples. This will kind of fit the same pattern as the parabolas and ellipses, where we have sort of a straightforward one where they ask us to do the completing the square process. That one's got big numbers. And then they give us some points that we'll need to then build the equations from. So first example will be the most straightforward example. Here we have y squared minus x squared. So that is going to be this up and down version of the hyperbola. So whatever it looks like, wherever it's located, it's going to be something like this. Okay, so we have y squared. There's no parentheses around it. There's no other quantity added or subtracted in with it. Same thing for the x. So what that means is that k, since there's nothing there, is 0, as well as h. H is 0. So this thing has a center of 0, 0. Okay. Then the quantity under the y is 9. So that will be a squared. So a squared is 9. B squared is 25, which means that a is 3 and b is 5. And then we'll go straight from there to find c. So c squared is a squared. And remember, we've changed that formula slightly back to the Pythagorean theorem. So c squared is a squared plus b squared. So that is c squared equaling 9 plus 25, which is not 36, it is 34. done this problem many times, and I've seen many people get that wrong. So like, oh, 36, it's a perfect square, good to go. No, it doesn't have to be a perfect square. That's okay if it's not a perfect square. The c value is the square root of 34. That's what it is. Remember that the c value is the distance from the center to the foci. So that one is not as important to be a nice whole number. We do like that the a and b are whole numbers. That way we can count to get those parts of the shape. The focus is a little less important in terms of drawing the hyperbola than the vertices or the center. Okay, so there we go. Let's go back up and see what else we need to find. So we found the center, we found the vertices, we've got the information to find the vertices. We have the information to find the foci. The t-axis is going to be x equals 0. The c-axis is going to be y equals 0. Now we need to get the asymptotes. So the asymptote lines are y minus k. So it'll be y minus 0. I know it's trivial, but I'll write it. Plus or minus a, which is 3, over b, which is 5, and then quantity x minus 0. So if we clean that up, it'll be y equals plus or minus 3/5 of x. And those are just lines that are sloped with a positive and negative 3/5. Okay, so I guess we should go ahead and now list out the vertices in focus because we haven't done that yet. So verts are h, which is 0, and then k plus a, so 0 plus 3 is 3. The foci are h, and then k plus c. C is the square root of 34. So the foci are, h is 0. 0 and then plus or minus the square root of 34. All right, the t-axis is x equals 0, and the c-axis is y equals 0. Okay, so that is everything. I guess we can label this asymptotes. That is everything that we need to find. So now we're ready to graph, and I'm going to go ahead and put the XY grid down. We've got our center there at 0, 0. Our vertices are at 0, plus or minus 3. So 1, 2, 3, and 1, 2, 3. Our foci are at plus or minus the square root of 34. So that is pretty close to 6. So 3, 4, 5, 6. Just underneath it. 3, 4, 5. No, that's 4, 5, 6. There we go. Just underneath it. Okay. So we are going to draw in the asymptotes before we draw in the curves. And the reason why we're going to do that, at least the way that I do this, it makes a box, and then you can lay your curve right on the edges of that box, and it makes the curve look much more exact than, say, when we were doing parabolas. So what we want to do, we're already counting up 3. What we're going to do is that slope is 3/5, and I know I could go and count and plot and dot lines. Here's the easiest way to do it. We already have the up and down, so we're going to go left and right 5 because that's the x movement. Okay, and then we are just going to make the corners of the box at those points. So there we go. And then we're going to just dot this box out. And then we are, and this is the hardest part of this, dot this line, this asymptote. And there we go. So my grid wasn't perfect, and I missed that corner right there, and that's going to happen when you don't have a perfect grid. So take your time, set it up better than I did, but there we go. So the box that I just created, I don't see that a lot of places. That's something that I do. I don't know where or why I picked it up, but that's something that I do when I draw these, and it makes it easier for me because from there, we know that the curve is going to hug that box very closely. It shouldn't really go inside of it, but it should get pretty close to it. It's kind of hard to draw on this screen like this, but There we go. So you'll see my lines are a little bit wobbly because when you press really hard on this, it gets a little wobbly. But the curve fits onto that box. So you'll see it just barely scrapes it at the vertices, and then the asymptotes keep it out of that area. And that is our hyperbola. So that's what we are looking to draw when we are graphing these. I would strongly recommend making the box. That is going to make it a little bit easier to lay the curve on. You're going to get a little bit better picture that way, and it demonstrates that you found the asymptotes, but it doesn't require you to graph two separate lines. You can just make the box and then connect the corners. It's the same thing really, but in my opinion, it's easier. Do whatever feels comfortable to you. That's the way that I like to set them up. Okay, so now we have the more challenging example. So it starts us off easy, then it goes more hard, and then it's going to get back to the easier version. We have to complete the square on this one, and they've done us a little bit of a favor. They have started with the constant on the right side, which is nice, but we got big numbers, and big numbers aren't a great thing for us here. So probably gonna have to break out the calculator on this one. It'll be the first time for this chapter that we've had to break out the calculator, but with these big numbers, it's gonna get some big products and sums, so we'll have to do that. Anyway, what we wanna do is we want to do what we've been doing. We wanna collect the x's, collect the y's, factor out anything we can, and then go through the completing the square process. So the x's are 25x squared and 100x. That negative stays with the 16 for the y squared, 96. Good thing is they do have common terms that can factor out 4, 4, 4. Unfortunately, we're so close to being able to just factor something out of everybody. We're very, very close to being able to factor out of 4, but that x squared term is 25, so we can't do it there. Before we even do this first step, since I've already done many of these, I know which orientation this is. The x squared term is positive, the y squared term is negative. I know that that is the left and right orientation since the x is positive. So that's a little hint starting out. We also know should know it's a parabola right away because it's a negative squared quantity. So that is two quick pieces of information we can get before we do any work really on this problem. Enough of that though, let's actually do some math. So what we want to do is we want to factor out what's common. If you want to pause and take a go at this, be my guest. The coefficients do get big, but you're more than welcome to give that a try. From this second part, what's going to happen here is we need to factor out the negative. So if you paused and tried and you failed on this and because you didn't factor out a negative, apologies. The negative has to come out. The leading coefficient on the y has to be 1y squared. So we need to pull out a negative 16, which is going to leave us y squared plus, oh gosh, 6? No. Yeah, 6. Minus 6. Okay. So we need to do that. And the reason for that is this parentheses, this factor needs to go down into a perfect trinomial square, and that does require the leading coefficient to be 1y squared, or else you're going to have to do a lot more work to complete that square. So factor out the negative, make sure that the leading coefficients are both positive 1 for the squared term. Okay, so those are now relatively simple squares to complete, 4 and a 6. Not too bad, those are small numbers. We'll do the process, they'll be small squares. The bigger numbers are going to come when we move to balance to the other side. So let's go ahead and start completing the square. So we have x squared plus 4x. To complete the square, remember we take half of that x term, so half of 4 is 2, and then we square that, so 2 squared is 4. To balance this, what I showed last time with the circles, instead of doing a plus and then a minus right away, I'm going to go ahead and start by just moving some more to the other side to balance. But for these, since there's a leading coefficient, remember we have to multiply the number that we're putting in by that leading coefficient. So 4 times 25 needs to go to the other side. So 4 times 25 is, of course, 100. So we're going to add 100 to the other side as well. Then we have minus 16 y squared. I'm going to run out of room, aren't I? Minus 6, that's okay. Y, so half of 6 is 3, and 3 squared is 9. So we are adding 9 times the leading coefficient, negative 16, to the other side. So that's 90 plus 54, so 144. But since this is a negative, we're going to add negative 144 to the other side. So again, we do the completing the square, and then which is half of that middle term, and then square that. Then we need to multiply it by the leading coefficient and put that number on the other side. So we multiply 4 times 25 gives us positive 100, and then 9 times negative 16 gives us that negative 144. Okay, so when we do that, now we get 400. Move that down just a hair. 400, and we have 25 x squared plus 2, so x plus 2, quantity squared. X plus 2 quantity squared minus 16 y minus 3 quantity squared. And then just like ellipses, we are going to divide by this number on the right as our next step. So we're going to divide everything by 400. 25 goes into 400 16 times. 16 times, that's nice. It's a perfect square as well. And then 16 goes into 400 25 times, I'm assuming. So I didn't actually end up needing the calculator. There we go. Equals 1. All right, so that's really nice that we got the nice perfect square numbers. That means our a value, a squared is 16, so a is 4. Our b value, b squared is 25, so b is 5. And then c is 16 plus 25, which is not a perfect square. That is 41. So c is the square root of 41. So it's very likely that your c value is not going to be a perfect square, and that's totally fine. So to graph this, I know we should probably list out all of the pertinent information. I'm going to graph this and then kind of glean that information as we go. So the center is going to be the opposite of what's in with each of the letters. So it's x plus 2, which means we're starting at negative 2 for the x. And then it's y minus 3, so we're starting at positive 3 for the y. Okay, so I don't know why I made a dark circle there. No, I shouldn't have erased that whole axis. Good enough. Okay. So that's our center point. Now we know this thing is opening left and right, so we're going to have a transversal axis that goes through this way. And the movement to the left and right is going to be 4. So we can go ahead and plot those on for the vertices. So 1, 2, 3, 4, and it's on that same transversal axis. And 1, 2, 3, 4 for this. And now to get the remainder of the box, I'm going to go up 5. So 1, 2, 3, 4, 5, and then down 5. 1, 2, 3, 4, 5. And then what I'm going to do is just going to go from underneath those big points and above those big points through the points on the way down. And I know it's probably a little faint on the screen, but the box is here. So to get the asymptote lines, we're going to connect the dots going through the center, hopefully. Oh, this one's not going to make it. That one was really off. Oh well, we didn't do a very good job there because they should pass through the center. It should be equal, but there's a lot of space right here compared to some of the other stuff over there. So this is a little off. Kind of got to fudge it a little bit. If I can get some of this to erase. but yeah, it should go through that and it should be there. So again, do a little bit better job. Maybe find a coordinate grid online, copy and paste it, or draw a better one, use grid paper. Mine's not super accurate. Apologies. Okay, so now we're just going to fit our curve into the box. So it's there and there, and we're set. So obviously you should probably take some time and write out the information like we did for the previous problem. The formulas are right there. So we have the center is at -2, 3. We have the vertices there at negative, what is that, 6, 3 and +2, 3. The foci would be at 2 plus or minus the square root of 41, comma 3 as coordinates. So those would be, out in here. Square root of 41 is close to 6, a little bit more than 6. So yeah, do a better job than I'm doing. I'm going through this kind of quick just to keep these videos short, but that is the gist of what we need to do. The hardest part there is, as always, completing the square process. Okay, one more example here, and for this one, we're going to start with a graph. So we have our xy coordinate plane. That's not a very good one. Let's try to make it perpendicular, and that's better. So our vertices are at -3, -6. So -1, 2, 3, 1, 2, 3, 4, 5, 6, and -3, -2. So I'm getting the vibe that this is opening up and down. And then the foci are at -3, -7. So just one more down. And then -3, +3. So one more up. So yeah, definitely this is opening up and down. Okay, so what we want to do is we want to find the center and then write the equations from this. So the best way to find the center, and this is true for an ellipse, basically what we have here are the same set of information that we were given for an ellipse. The difference here is the vertices are closer together and the foci are farther apart. So if it were an ellipse, the vertices would be the farther and the foci would be in the middle of them. So that's the really big difference, and I showed that little almost example of turning the halves of the ellipse outward to make the hyperbola. Anyway, the best way to find the center is to average either of these two sets. So average either the verts or the foci. Doesn't matter which one you do, you'll get the same result either way. So if we average the vertices, -3 is the x-coordinate. Doesn't matter if you average that, it's still going to be -3. So we're really just concerned with the y-coordinate. So -6 plus 2 over 2 is -4 over 2, which is -2. So that is the y-coordinate is -2, and the x-coordinate is the same for all of these. So the x-coordinate is -3 throughout. That's going to be true for the center because they're all on that same transverse axis. So we go to -3, -2, and if we did a good job, it should look like it's in the middle. I'm kind of fudging it because I didn't do a very good job again. But there we go. It is the center at -3, -2. Okay, so now what we want to do is we want to find A, B, and C so we can write the rest of the equation. We don't really need C for these equations because we already have the foci. So to get the vertex form of the equation up here, we really just need A and B. So A and B, A we can get off of the graph, B is going to come from the equation here, so I guess we really do need C. Okay, so A is the distance from the center to the vertex, and that's from this part of the equation right there. So the center is at -3, -2, and the vertices are at -3, -6, and -3, +2, which means that those are a distance of 4 away from the center. From -2 to 2 is 4, from -2 to 6 is 4, so they are 4 away from the center. So our A value is 4. The c value is the distance from the center to the foci, so from -2 to -7 or from -2 to 3, that's going to be 5. Since we were given this foci information to start, they made them nice numbers, not the square root of 41, nice whole numbers, so the rest of the problem would work out a little bit better for us. The last thing we want to do with this set of numbers is find b, so we are using c squared equals a squared plus b squared, so c squared is 5 squared equals a squared, so 4 squared, plus b squared. This is a Pythagorean triple. We are going to get a nice whole number for b. We don't have to. They don't have to give us a nice number for b. B is going to go into the equation as a square, so if b is the square root of 26, it doesn't matter. When we write the equation, it'll be y quantity over 26, because it's b squared that goes in the equation. So this does not have to be a perfect square, just like c in the previous problems did not have to be a perfect square. It works out for us that it is this time, but that's usually not the case. So b squared is 9, so b is 3. Again, that's a Pythagorean triple, so hopefully you recognize that. If not, do the math, it works. Now we're ready to write the formulas. So it's going to be the up and down version. So that is the y first version. So we're going to have y squared, quantity at least, y minus the x quantity equals 1. Okay, so now we need to put in the center, and it's going to be the opposite. So if the center is at the y coordinate -2, that means we're going to put plus 2 into the y parentheses. Same thing for the x. Since it's at -3, we're going to put in plus 3. The y squared will be over the a value squared. So the a squared value is 16. We know that a is 4, so that means a squared is 16. And then the b squared value is 9. So there we go. We have the formula for this hyperbola. And of course, we can draw in the remaining. We know now that b is 3, so I can go 1, 2, 3, and that's the corner of my box. 1, 2, 3, there's the corner there. Corner and corner, and that is going to be our box where our asymptotes will pass perfectly through the center from corner to corner, because I did a decent job this time. And there we go. So we fit our hyperbola onto that. This one's probably the most narrow of the examples we've done today. And there we go. So that's the graph, that's finding the equation, and of course we could fill out the rest of the sets of information. We already have the vertices and the foci, so writing the center, we've got that. So you could still have to do the transverse axis, the conjugate axis, and I think that would about wrap it up since we already have the A, B, and C as well. Okay, so those are the different ways that they can present the problem to you, which are the same ways that the rest of the conic sections have been presented to us. So the big takeaways from this is the same amount of work that we've been doing, the same style of work that we've been doing. The equation is ever so slightly different from ellipses in the fact that it is a squared minus a squared, which is the first time this has happened, and that is the unique identifier you use to say, oh, hey, that's going to be a hyperbola. The other big key difference is the CAB relationship. It is now c squared equals a squared plus b squared. And then to close this out one last time to reiterate what the differences from the equations are. Parabolas have one variable squared. That's how you know it's a parabola. Ellipses are both variables squared added over some number equaling 1. Circles are both variables squared equaling a number that's not 1. And hyperbolas are the only one that have a subtraction sign anywhere in the problem. So it's quantity minus quantity, both squared equaling 1. That'll do it for this video, and that will do it for conic sections.